Is it good? Oh. Okay. Okay, I think we can get started. Today we're going to talk about GPU architectures. Everything is fine online? Okay. GPU architectures. We're going to build on SIMD processing that we covered last time. And clearly this is a fascinating topic. GPUs are parallel computers that you have in your pocket that nobody had the luxury to have in the past. People used to build supercomputers that are much less powerful than today's GPUs. Today you have it in your pocket. So you can imagine the computational power we have today. It's fun to learn about GPUs. But I'm going to first remind you about what we covered, SIMD processing. And then we're going to talk about SIMD operations in scalar ISAs or von Neumann architectures. So von Neumann architectures actually incorporate SIMD operations as well, as we will see. And then we're going to jump into GPUs. So you can see the impact of SIMD processing everywhere in our lives. Okay, these are some readings. And this is where we will start. Remember, SIMD processing is all about single instruction, multiple data. We're exploiting regular data level parallelism. And we discussed the seminal paper that divided the computing spectrum paradigms in terms of the instructions and the data on different axes. And single instruction operating on multiple data elements falls into SIMD. And we discussed two types of pure SIMD processors, array processors and vector processors. And I mentioned in last lecture that existing GPUs combine both of these types. So this is really a purest distinction today. Existing GPUs are both array processors and vector processors. If you get the trick question in an interview, for example, so if someone asks you, is GPU a vector processor? You say yes. Is GPU an array processor? Yes. Except it's programmed in a completely different way, as we will see today compared to traditional SIMD. And just to jog your memory, what's an array processor, what's a vector processor? Essentially, these both operate, have multiple processing elements, and they can execute multiple instructions at a given time. Except array processor has much more powerful processing elements where each processing element can do any operation. And this way, you can actually execute the same operation at the same time on all processing elements on different data elements, different data inputs. You can see that at a given time, all the processing elements are executing loads in the first cycle, adds in the next cycle, multiplies in the next cycle, and stores in the next cycle. Vector processor is more frugal, meaning the processing element can be simple, as we discussed. You can have different processing elements specialized, load unit, add unit, multiply unit, store unit, for example. Each unit doesn't have to do everything, and that's why it's actually easier to build. But here, you cannot execute the same operation on multiple processing elements at the same time, you have to pipeline it over time. But if you look at space, you basically execute one operation in the same space, but different operations in the same time. That's how you exploit the parallelism, basically. And in real processors, we combine both of them. And we said that SIMD is very powerful because it enables a single instruction to specify huge amounts of work, because you're doing the same operation that's specified by the instruction on many, many elements, billions of elements potentially, right? Maybe you can turn off the admitting over here. I don't know why Zoom has this. Yep. I can hear myself here also. Okay. Yeah. Basically, this is a bad design in software, as you can see, right? The software should not really interrupt the presenter. Why should the presenter be admitting some person over there, as you can see, right? Okay. So there are design principles you can see, and this is broken in this piece of software, if you will. Okay. So basically, you can see that vector processors are more frugal, but both of them really execute a lot of operations. Okay, well, what was I saying? Basically, a single operation specifies a lot of work. This way, you don't need to decode, fetch the same instruction many, many times, right? I mean, you've seen that. But because of the same reason, a single operation specifies a lot of work on a lot of amounts of data, large amounts of data. We need a more powerful memory system. And the remaining 6 lectures, we're going to talk about the memory system. And 6 lectures are really not enough to talk about the memory system, as we will see. This is really the most important part of today's machines. And a GPU has a very sophisticated memory system. And we talked about vector processor memory system. Basically, we said that you need to be able to sustain n concurrent accesses if you actually want n elements at a time. In an array processor, you need n elements at a time if you're doing a array load, right? Vector load on an array processor. And we will see that GPUs actually exacerbate this because they follow the same paradigm. Okay, you remember memory banking? We're going to revisit that next week, probably, maybe tomorrow. Okay, so this is how we combine the paradigm. So you have a vector addition instruction, and this is how it's executed on a vector processor. It's executed on an addition unit this way. Each let's say, element of the vector is operated on in consecutive cycles in time. But now you can actually do both space and time in a combined array and vector processor. You can see that the first 4 additions of the first 4 elements are done concurrently across different 4 add units. And then the next 4 elements are pipelined. Next 4 elements are pipelined. Next 4 elements are pipelined. So this is basically an array processor where the array width is 4, and then a vector processor also where the vector length is specified somehow by the vector register. Okay, you've seen all of this, and we've discussed that this enables us to divide the register file such that elements 0, 4, 8 come from this piece of the register file, elements 1, 5, 9, ... come from this piece. This way you can have partitioned vector registers as opposed to having a huge monolithic register file, which makes the design easier. It also clearly improves your parallelism, and this is called the vector lane. And we're going to see that a GPU is going to be very similar to this soon. I'm just going to change the terminology a little bit. So these 2 pictures, this picture and this picture, keep that in mind. You're going to see it again. In fact, this picture, you're going to see it again also. Here, the terminology is vector processing or SIMD processing. You can overlap the execution of multiple vector instructions. So in this particular case, you have 32 elements per vector registers and 8 lanes. You have 8 load units, if you will. You can do 8 loads per cycle. And how do you actually do 32 loads per cycle? You start the remaining loads in consecutive cycles. One single load operation does 8 loads in one cycle, and the vector length is 32. So it basically launches 3 more batches of 8 loads. And then you have multiply, and then you have add, and then if you have another load, it starts another 32 operations. And you can see that these are both pipelined and parallel. This way you can sustain 24 operations per cycle in this particular example. If you look at time, at a given point in time, in the steady state, you have 24 operations going on 24 different data elements. Okay, these are all review. We've seen this. We've also seen the disadvantage. We've talked about the advantages, so I'm going to focus a little bit more on disadvantages here. This works nicely if parallelism is regular, right? If you have a data parallelism or SIMD parallelism, what's called, operating on very large vectors, this is great. Unfortunately, if parallelism is irregular, you have problems. It's very hard to get efficiency out of this machine. It's a general purpose machine, so it can actually work. You can actually program it. You can actually write any program with this. But unfortunately, the efficiency is very low. Your SIMD vector length can be, let's say, 32, but you may be utilizing only one. So you may be running scalar code on a vector processor, and that's clearly very, very inefficient, right? That's why people have built special scalar units inside the vector processor, such that those scalar instructions do not get executed on the expensive part of the processor. Okay, and I've also given you this quote from Josh Fisher on VLIW, and he's absolutely right in what he says over here. We've discussed that last time. And we've discussed that you can actually, if your program is nice, you can automatically vectorize your program. For example, if you have this loop, which is vectorizable because loop iterations are independent of each other, you can execute it like this. We're going to see this actually very soon again, in a scalar machine. Or you can identify that loop iterations are independent of each other by doing some analysis on the program using compilation techniques called loop dependence analysis. You can basically parallelize the iterations. So basically you put the iterations together, multiple iterations together, let's say vector length iterations together, and then each instruction is a vector instruction over here. This green instruction is a vector load. This brown instruction is another vector load. This pink instruction is a vector add. This yellow instruction is a vector store. And you're doing 32 iterations in parallel using vector instructions. So it's beautiful. Okay, just to summarize, we've also discussed this. This is very good at exploiting regular data parallelism. And performance improvement, unfortunately, is limited by the vectorizability of code. So I'm going to remind you of Amdahl's law again. And this is what we're going to cover next. Many existing ISAs include SIMD operations. They don't go full way of actually having a full SIMD processor inside the von Neumann machine, but they actually have instructions that operate using the same principles, as we will see. So before that, we should always remember Amdahl's law. If someone says Amdahl's law doesn't exist, you know what to say. As long as you have some sequential code, as long as your f is not 0, you're bound by, f is not 1, f is a parallelizable fraction of a program. As long as if f is not 100%, you are limited by the speed up that you're going to get. So you want to make a parallelizable fraction of a program using algorithms or different compilation techniques as high as possible. If it's not high, you know that you're dominated by this part of the speed up equation. Okay, we'll see this again very soon with the GPUs. Any questions? This was a very quick overview of the last lecture. Now we're going to jump into how last lecture applies to modern processors in your pockets again. Basically, modern processors, von Neumann machines, have single instruction, multiple data extension instructions. Essentially, these are special instructions where the instruction acts on multiple pieces of data at once, as opposed to acting on 2 registers, register 1, register 2, one piece of data, each one element. You basically act on 4 elements at a time. Here you can see an example at the bottom from an earlier Intel multimedia extension instruction. And why were these introduced? As your suggested, recommended reading describes very clearly, people wanted to accelerate graphics, multimedia, image processing applications that have been becoming more popular in the 1990s. Essentially, they did not want to change the ISA significantly or the execution model significantly. So they basically added these instructions that can perform short arithmetic operations, also called packed arithmetic. So if you look at this example, it's a packed add 8. What does that mean? Basically, you're adding 4 8-bit numbers in a packed register. Register is 32 bits itself. Each element that you're adding is 8 bits each. And you have 2 registers, as you can see. Register 0, S0, register 1, S1. And you can see that this operation's result is add the bottom 8 bits together and put the result at the bottom 8 bits of register S2, destination register. Now do the same thing for the next 8 bits for each of the registers and put the result into destination register's next 8 bits and keep doing the same thing. You can see that this is a SIMD operation, right? Single instruction operates on multiple data elements where the data elements each happen to be 8 bits. And the good news is you can modify a 32-bit ALU adder very easily, chop it up into 8-bit pieces, ignore the carry operations such that they don't actually feed into the next, let's say, 8-bit chunk. This is actually almost 0 cost, if you will, in terms of the additional hardware you add. So it's beautiful, as you can see, right? Of course, if you want to have a larger vector length, if you will, in this case, the vector length is only 4, if you will. It's not specified because it doesn't exist. Vector length doesn't exist because this is a single instruction saying this single instruction operates on 4 data elements. That's it. There's no vector length or anything, as we will see in the next slide also. But if you want to actually increase that, if you want to actually operate on 64 elements at a time, your register needs to become wider. So it looks more like a vector register at that point, right? If you want to increase, if you want to operate on 64-bit elements at a time, well, you cannot do it in this case, right? If your registers are only 32-bit wide, clearly you cannot do it. So it's limited in what you can introduce. So this was introduced first by Intel in this, as this paper describes. Basically, they called it the multimedia extension operations initially. Now it's named something else, as you will see soon. But basically, a basic idea is SIMD. One instruction operates on multiple data elements simultaneously. In this sense, it's really very much similar to array processing, right? This is not a vector processing. If somebody asks you the question, does this look like a vector processing instruction? No, it's really array processing because you're really operating on 4 elements at the same time, right? And as I said, it's designed with the multimedia operations in mind. So let's take a look at this example over here. Here we have a 64-bit register. Clearly, in a scalar operation, you can actually add 2 64-bit values by referencing 2 registers. That's a scalar operation. But there are instructions added into the instruction set architecture that can treat the 64-bit register as 2 32-bit data elements, so that you can actually add 2 32-bit data elements, or as 4 16-bit data elements, such that you can actually add 4 16-bit elements, or 8 8-bit elements, so that you can actually do 8 operations or 8 adds per cycle on 8-bit bytes, basically. So that's the idea, and it's beautiful, as you can see. There's no vector length register. The opcode is different for each of these instructions. An opcode determines the data type, whether you're operating on 8 8-bit bytes, 4 16-bit words, 2 32-bit double words in Intel terminology, and 1 64-bit quad word. And if you're doing a load, etc., stride is always equal to 1. These are basically consecutive. Okay. Does this make sense? Hopefully it's simple, right? And the operations are very similar to vector instructions. So these are the instructions that you can see. This is called packed, compare, greater than word. So basically you have 4, you chop the register into 4 words. And let's assume that this is the source register, and these are the values of the 4 words in the source register, and these are the values of the 4 words in the second source register. The result of this operation is this. Let's take a look at the ISA definition. Compares packed 8 bytes. Well, in this case, I think 4 16-bit words. Result is mask of 1s if true or 0s if false. So you basically compare 51 to 73. 51 is not greater than 73, so the result is all 0s in these 16 bits. 3 is greater than 2, so the result is all 1s in these 16 bits. 5 is greater than 5. No, that's not true, so the result is all 0s. 23 is greater than 6, so the result is all 1s. So now what you're seeing here is you're creating a mask. Remember the vector mask register? We had that as a special register in a SIMD processor. Well, we have it in a general purpose register over here. The destination register specifies the mask. And we're going to use that as a data element to actually decide which operations take effect or not by programming this in a nice way. Does that sound good? Okay, so you can see there are many, many operations. These are actually more advanced. At the time, this is 1990s. They basically add the packed, multiply, add, word to double word. So basically you have a very similar view of the same register, 4 16-bit words, another 4 16-bit words. What this instruction does is, it basically does this operation. It's multiply and add. It multiplies the corresponding 16-bit words. A0 times B0 goes over here. A times B1 goes over here. A2 times B2 goes over here. A3 times B3 goes over here. And then it adds the top parts. Basically, this is the addition, and this is the addition. Why? You can actually do a matrix vector multiplication using these operations, as we will see in the bottom part. So you can see that you can actually do matrix multiplications. And this is how they describe how to do it. I will not go into this in detail, but you need to do these operations. This is called the packed, multiply, and add, word to double word. Unfortunately, the instructions are very ugly, as you can see, but they make sense. You basically do this multiplication addition, and then you do another packed add so that you can actually reduce the adds so that you can do the matrix vector multiply. If you're interested, you can read the paper for more, but it's not magic. It's all doable with instructions, as you can see. Okay, let me give you another example. This is the image processing example that they provide in this nice paper. Unfortunately, they don't have colorful images in this paper, so we tried to add a little bit of color. basically, these are the types of operations they were targeting. Essentially, you have this image X, let's say, and then you have a background image Y, and there's a blue background in image X. Now, the idea is to replace that blue background, doing some image processing, with some blossom background. It looks like a tree over here, and then obtain this image. So this is standard image processing, very, very simple operations, if you will, by today's standards. But if you don't have parallel operations, it's actually slow. So this is the loop that you would write to do this. You go through every pixel in the image. You check if the source pixel is blue. If it's blue, in the new image, you replace it with a pixel coming from this second image. That's the idea. Otherwise, new image stays the same as the original image, right? That way, you will have this lady behind a nicer background of trees as opposed to a blue background. Okay. So how do you do this with scalar operations? Basically, this becomes all scalar. It becomes all scalar, but with MMX, multimedia extensions, you can operate on 8 pixels at a time, essentially, assuming each pixel is 8 bits. And you can see this nice instruction that we saw earlier, packed, compare, equal, byte. Basically, you load 8 pixels of this image in MM1. That's the register name. Assume that all of them are blue over here. Nice. And then you basically, this is MM1. This is basically you're comparing everything, whether it's blue or not. This is basically the thing that you're going to try to mask with. And then you load 8 pixels of this image into MM3. And some of them are blue and some of them are not blue, as you can see. These are coded. And what this instruction does, it compares whether the value over here is equal to this value or not. So, and then the result is a bit mask. So if these two 8 bits are equal, you'll get ones over here. In this case, they're not equal because this is blue and this is not blue. It's encoded some way, of course. These are zeros. So these two pixels over here are not blue, so you get zeros in the bit mask. These 2 pixels happen to be blue, so you get all ones in the bit mask. And these 2 pixels are blue, you get zeros, and these are not blue, and you get zeros, and these 2 pixels are blue, and then you get ones, as you can see. Okay, so how do you take advantage of that bit mask now? Basically, remember what we were going to do is we were going to take the blossom image and replace the original image when original image actually matches the blue parts. So if the bit mask is 1, in the final image, we should actually, the pixel should come from the blossom image. If the bit mask is 0, in the final image, the pixel should come from the original image. Makes sense, hopefully, right? And this is what these instructions essentially do. Basically, you take the blossom image, 8 pixels at a time again, and then you end it with the mask, and then you get a result. And this is a partial image that contains the pixels that are blossom, as you can see. Everything else is zeros. And then you take the original image and end it with the mask. And not with the mask, because basically you need to pass the pixels from the original image, which are marked in red over here. So if the mask is 1, the result is 0. If the mask is 0, you pass the original image pixels. That's why this is and not. Okay, and then you basically OR these two things. And hopefully, because of the way we have constructed the program, in the final image over here, or final 8 pixels of the image, you have the blossom image in places that were blue in the original image, and you have the original image in places that were not blue in the original image. That's the idea, okay? So you can do this essentially with this instruction sequence. These are loading 8 pixels from the original image and then the blossom image to 2 registers. And then you do the pack compare equal, which sets the mask in MM1. And then you do the packed end to get the blossom image in appropriate locations. And then you get the packed end not to get the original image in appropriate locations. And you OR them into registers so that you can actually construct the final 8 pixels on the image. And then, of course, you need to iterate. If the image has 1,000,000 pixels, you have to go through all of them 8 at a time, right? But you can parallelize it right now. Before, you were going through 1 element at a time. Now you're going through 8 elements at a time. So hopefully you can speed this up by close to 8x, right? Assuming it's perfectly vectorizable. Well, it is perfectly vectorizable, but then there's some serial code that you may need to deal with clearly, right? Does that sound good? So it's beautiful, as you can see. It's not magic, but it's very similar to what we have done earlier, except we didn't deal with vector length, because vector length is encoded in each instruction. And we dealt with vector mask in a very different way, right? Vector mask is really a general purpose register over here. And we use it as part of the operands to the instruction. Okay, you can read this paper, but basically they say that MX speed up computation intensive inner loops or subroutines on average between 3 to 5 times. And they give some examples. For example, an MPEG-1 video decoding application at the time. Today we're actually much further. We are beyond MPEG actually in many cases. On a Pentium class processor with MX technology executes 1.5 times faster than the same application on the same processor, not using the MX technology. And then you can see that Intel plans to implement MX technology on future Pentium and Intel architecture processors, blah, blah. And they believe that it will scale well with CPU operating frequency and future Intel microarchitecture generations. So you can see that these folks actually were prudent to write this paper at the time, right around the time they were actually releasing it. So it's good that people are doing this. In fact, if you know the backstory at Intel, this was actually a very controversial thing to put out, because they said, we're changing the ISA significantly. Who's going to use these operations? And then the people who are, let's say, more progressive won. They said, release it, and there will be a lot of people, because this is actually used in many systems. And clearly, they did the right decision at the time. So this is always a decision, right? You put something into hardware, will people use it? A lot of companies worry about that. If you actually have good evidence that there are a lot of applications that may potentially use it, then go for it, right? And today, actually, people don't use it just for graphics. We do a lot of research in bioinformatics, for example. There's a lot of parallelism that you do when you compare different genomes. You basically can use all of those operations very nicely when you compare different elements. Text comparisons, for example, clearly machine learning also. So these extensions have improved a lot over time. I will not go through this, and you don't need to clearly know all of this, but initially you had 64-bit MX registers. Over time, Intel changed their names, like streaming SIMD extensions for marketing purposes, etc. Basically, they added a lot of new instructions, like shuffle operations and double precision floating point operations, larger registers so that you can exploit parallelism. AVX extensions are also the older version right now. Now you could operate on 512-bit things. Now 512 bits is, if you're operating on 8-bit values, that's 512 divided by 8, right? That's 64 elements at a time. If you're operating on 64-bit values, still 8 elements at a time. Not bad, right? But of course, think about 512 bits now. Now your memory system needs to support all of that as well. And more recently, Intel introduced these advanced matrix extensions like everybody has been introducing, right? Here you have 2-dimensional registers and a tiled matrix multiply unit, and you can read about it also. Basically, this supports matrix multiplication. And we're going to see that GPUs also introduce these specialized units soon, even though they're SIMD machines. Okay, any questions? We're still talking about extensions, not GPUs yet. But let me give you an idea of SIMD operations and their popularity. Other machine learning accelerators take advantage of SIMD operations as well. We've talked about Cerebras' wafer scale engine. I'm going to very quickly go over a very brief overview just to show you that this actually takes advantage of multiple paradigms. So they have this number of cores, and they map a neural network onto a whole wafer. And basically, they have many processors to map things onto. So you cannot see all the processors over here, but it's literally multiple instructions operate on multiple data elements. It's a multiprocessor, multiple instruction, multiple data machine, as we may see later on also again. But you're operating, you have basically different programs running on different processors. But if you look at each processor, so this is basically this is the MIMD machine. It's actually very interesting. It incorporates some concepts that are more advanced for this course, but for future courses, we cover a lot of these. Basically, you connect many processors using a 2-dimensional mesh interconnection fabric such that they actually communicate with each other. But each processor looks like this. You can see that there's a floating point multiply and accumulate unit. And you guessed it's a SIMD unit. Basically, each of these have some memories and they communicate with each other. But each of these processors is a SIMD processor actually. It has 4-way SIMD for 16-bit floating point operands. Not very powerful, You can do 4 floating point operations per cycle. And it has a local memory as well. And you can do floating point multiply and accumulate. And the basic idea is you map your neural network computations to these floating point multiply and accumulate operations. Very similarly how we did with systolic arrays, except this is a SIMD machine right now. Remember that picture that I showed you when we talked about systolic arrays. You can convert a convolution to a matrix multiplication. Essentially, that's what they're doing. They're converting convolutions to matrix multiplications and doing them using these four wide vector operations or SIMD operations. Okay, if you're interested, there's a lot more out there that talks about this. But I wanted to point out that SIMD operations exist in machine learning accelerators, specialized for machine learning as well. Now let's jump into GPUs. How many people have programmed GPUs here? Okay, I think I asked this question somewhat before. Not many. Hopefully you'll program them, it's fun. They need to be a bit better programmable. But basically, GPUs are SIMD engines underneath. What we've discussed apply to GPUs. I'm going to show you how it's different in GPUs. The instruction pipeline operates like a SIMD pipeline. In other words, like an array processor, as we will see. However, the programming model is completely different. It's not done using threads. It's not done using SIMD instructions. It's done using threads. And we're going to see this in a little bit. So let's go back to our parallelizable code example, which I really like. But before going to that, let's distinguish between different things. Programming model in software versus the execution model in hardware. So these two things are very different things. And we've seen examples of this, right? You can have a von Neumann-based scalar ISA programming model, sequential code, and you can execute it data parallel, right? We converted the von Neumann program to a SIMD program in the earlier lecture. Data flow, we've discussed this. And multi-threaded, you break things into threads. How many people have done multi-threaded programming here? Okay, I expect more people. That's good. So multi-threading, you break the program into tasks, basically, and parallelize them on multiple processors or multiple threads, hardware contexts. Now, execution model refers to how the underlying hardware executes the code underneath. It doesn't have to do anything with the programming model. Of course, if it matches the programming model, that's better, right? Because you can exploit the type of parallelism expressed by the programmer. But it doesn't have to. So, for example, you can have out-of-order execution, like we have seen, vector processing, array processing, data flow processing, multiprocessors, multi-thread processor, etc. An execution model can be very different from the programming model. For example, von Neumann model is implemented by out-of-order processors today. Underneath, the execution model is not sequential, well, strictly, right? Underneath it's data flow, as we've discussed, except because you have to obey the contract, you have to eventually give things back sequentially to the software, as we have discussed, right? A GPU is somewhat similar. It implements some model. Programming model is called SPMD, as we will discuss, single program, multiple data. It's a version of multiple instruction, multiple data programming. But it implements, GPU actually executes this code on a SIMD processor, single instruction, multiple data. Now, this may sound like magic, but basically, GPU takes advantage of the fact that there are many threads executing at the same instruction. And it gathers them together somehow. Because the programming model first expresses it nicely, as we will see. And even if the programming model doesn't express it, GPU can actually gather many threads together that are executing the same instruction and put them into the pipeline. Okay, so let's take a look at these examples. This is our code, very simple, vectorizable. And this is the scalar sequential code. This is how you might program it, right? I don't show the instructions, but you can imagine what the instructions are, and we don't have the branches clearly over here. So let's examine 3 programming options to exploit instruction level parallelism in this sequential code. Sequential, single instruction, single data, data parallel, single instruction, multiple data, and multi-threaded, multiple instruction, multiple data, or SPMD, as we will see. Now, sequential looks essentially like this. There's a branch also, etc. This can be executed. Hopefully, you can write the code, sequential code, MIPS code, for example, for this. This can be executed in a pipeline processor, right? It exploits some instructional parallelism. We've seen that. This can be executed in an out-of-order execution processor. what out-of-order execution processor does is it can find out that these two loads are independent, right? It can execute them together. It can also find out that this add is independent of anything else over here. It can execute that. So out-of-order execution, by looking down in the instruction window, it can find that all the independent operations, theoretically, basic independent instructions are executed when they're ready. And the big benefit of out-of-order execution in this piece of code, this kind of code, is different iterations that are completely independent of each other. We know that. Out-of-order execution does a lot of work to find that out. It doesn't even find that out, right? It just finds out which instruction can be executed when. That's it. But the end effect is that it can take all of these different iterations in the instruction window and it can execute them in parallel in multiple functional units. So it's really parallelizing. It's really taking advantage of the fact that these different iterations are parallel. And also, even within an iteration, there's parallelism between instructions. So in other words, the loop is dynamically unrolled by hardware. If you have heard of the term loop unrolling, you basically unroll the loops. You don't need to know that, but essentially, dynamically, the hardware is unrolling the loops, iteration by iteration. Okay, a superscalar or VLIW processor, which we have seen also, goes to the next step, right? It's orthogonal to out of order, actually. Both of these concepts are orthogonal to out of order. But basically, you can fetch an instruction, multiple instructions per cycle. Same iteration, different iterations, doesn't matter. You could do that. Okay, so you can using the scalar sequential code, we've seen a lot of paradigms to accelerate it. VLIW, of course, does the compile time analysis to figure out which ones can be executed in parallel and packs them together, and then executes different operations in parallel in a given cycle. So that's good. And we've seen all of these paradigms. Let's take a look at SIMD. We've also seen SIMD. We know that these these iterations are independent of each other. So we can actually vectorize them or create SIMD instructions. So you put a bunch of iterations limited by the vector length in the end. Either the programmer or compiler generates a SIMD instruction to execute the same instruction from all iterations across different data. Basically, this is a SIMD instruction, right? You realize instructions, iterations are independent. These loads can be executed in parallel, and only a single load instruction can express a vector instruction. So vectorized code looks like this. This is a vector load, A goes to V1. Of course, you need to have a vector length specified, right? But we are assuming that N is large, so you can actually have a huge vector length, if you will. And then the next load is another vector load, B goes to V2, vector register 2. The next vector instruction is a vector add. You add V1 and V2, the result goes to V3. The next instruction is a vector store, V3 goes to C. It's beautiful. What we have just done is automatic code vectorization, basically. The compiler needs to do the hard work to actually make it happen, but the compiler can do it in this easy piece of code because you can see that there is no dependence across iterations, right? This is a very easy to analyze code. So this is best executed by a SIMD processor, a vector and array, and we've seen that. We've seen that you actually have only 4 instructions over here. Beautiful. Now, the same code, you can execute it as multi-threaded. Basically, each iteration is independent again. We're going to take advantage of that. And we're going to say different iterations are executed by different threads, right? Programmer or compiler generates a thread to execute each iteration. Each thread does the same thing in this particular case, right? But on different data. But sounds good. You can execute this in a multiprocessor also, right? You can basically say each iteration goes to a different core. And all of the cores execute, and of course you need to have some, in the end, something to make sure that everything is done. So this can be executed in a multiprocessor nicely, and if you have 1 million iterations, 1 million of them can go to 1 million different cores. Sounds good. And cores can be very simple potentially, right? That's the beauty of potential multi-processors. Now we're going to also realize that there's a special aspect of this particular model. Here, each iteration does exactly the same thing. Meaning each thread does exactly the same thing on different data elements. Exactly the same thing, meaning that they have exactly the same code. This doesn't mean that they execute exactly the same operations, clearly, but they execute the exact same code. There may be branches, so they may actually change what they execute. We will see that. That will complicate things. But because each thread has the same code, this is also called a single program, multiple data paradigm. You have a single program, you replicate it, and each of them operates on multiple different data elements. And it can be executed on a SIMD machine. And that's what a GPU is basically. A GPU is programmed using the single program multiple data paradigm. And a GPU acts like a SIMD machine. Whenever it realizes that these threads are actually executing the same load, it combines them. Okay, so this is also called single instruction multiple thread in NVIDIA terminology. Not a bad terminology, I think. Basically, single instruction comes from multiple threads at a given time. So basically, a GPU is a SIMD or SIMT machine, except it's not programmed using SIMD instructions like we did yesterday. It's programmed using threads that everyone is familiar with. SIMD is a bit harder, if you will. But the threads need to obey this SPMD programming model. Each thread executes the same code, but operates on a different piece of data. Now, this looks very nice for graphics, right? Remember the image? We're doing the same operation, same set of operations on many, many elements of data, right? That's why this fits nicely. Each thread has its own context. It can be treated, restarted, executed independently. That's a benefit over here. It's more flexible than a SIMD machine. In a SIMD machine, it's very hard to change the vector length, for example, easily. So a set of threads executing the same instruction are dynamically grouped into what is called a warp. This is NVIDIA terminology. Wavefront is the AMD terminology. I'm going to describe this in a little bit. But basically, the hardware groups these threads that are executing the same instruction, meaning that are at the same program counter. Of course, initially, this is easy if your programming model expresses this, right? And it does. But you can do more. So a warp is essentially a SIMD operation formed by hardware, as we will see. So let's take a look at this. So let me define warp. Warp is a set of threads that execute the same instruction, i.e. at the same program counter. So this is warp 0 at PCX, assuming the program counter of this load is X, right? Because these different threads are executing the same code. They're both at program counter X. They're fetching the code from the same location in memory base. And this is warp 0 that goes to the next instruction, PCX plus 1. This is warp 0 that goes to the next instruction, PCX plus 2. And warp 0, PCX plus 3, okay? So basically, you can treat these different threads that are executing the same operation as a set of warps that execute the same operation. Okay, we're going to see how that is executed soon. So basically, graphics processing units are SIMD that are not exposed to the programmer, if you will. Threads are exposed to the programmer, but underlying, we do something else. So let me discuss this a little bit more. What is SIMD? SIMD, what we have done last week, we have a sequential instruction stream. Actually, we did it a few minutes ago also. We have a sequential instruction stream of SIMD instructions. Vector load, vector add, vector store, right? We've seen that earlier. Each instruction specifies multiple data inputs. You need these instructions, and you need a vector length. I'm ignoring the vector mask for now. We're going to treat that interestingly soon. Whereas SIMT is multiple instruction streams, multiple threads, in other words, of scalar instructions. So what you do is really sequential scalar programming. You don't need to think about a vector length. You just say, this is the code I want to execute on a single element. And if I happen to execute this code on 1,000,000 elements, that's great. I'll specify the size of that block and execute this code on that 1,000,000 elements. I don't need to deal with vector length. I don't need to deal with vector mask. GPU will do that automatically. Okay. So basically, this is what we do. These are scalar operations. I don't care about vectors. Load, add, store, just like I program a sequential von Neumann machine. And I say number of threads. Well, we will see number of blocks, actually. So there's a little bit more over here, but it's the same thing. So what are the advantages of this? So we just changed some things, but this brings about huge advantages. And this is why GPUs have been hugely successful, whereas traditional vector and SIMD processors or SIMD processors have not been that successful. Again, it's all about the programmer. What you expose to the programmer. Programmer can program in von Neumann. Let's say they're not that educated to program in something much more sophisticated. They're not that used to, in other words. Well, this is von Neumann, extend just a little bit, right? That's the idea. Hardware does the harder task. So, okay, so the two major advantages is, first, you can treat each thread separately. In other words, you can execute each thread independently on any type of scalar pipeline. You can do actually multiple instruction, multiple data processing. You can have a multiprocessor, and GPUs exploit that also. And you can also group threads into warps flexibly, meaning you can group threads that are supposed to truly execute the same instruction. You can dynamically obtain and maximize benefits of SIMD processing. This is actually very, very interesting, because if you find out that, okay, I have 64 threads lying out over here. They're executing, I have 20, let's say 20 threads that are lying out here. You need to keep track of this, of course. they're executing program counter X, and they're supposed to execute program counter X. And I have another 40, let's say 44 threads over here. You can combine them, and you can have a 64 thread execution to maximize the SIMD parallelism. And we're going to see that soon. So let's start with the first one. How can we treat each thread separately? Or what benefit do we get from this? You remember the notion of fine-grained multi-threading, right? We're going to go back to this. We're going to basically do fine-grained multi-threading of these threads on a very simple pipeline, scalar pipeline. So assume that we have a warp that consists of 32 threads, because somebody actually specifies that, right? If you have 32K iterations, because this is the hardware limit, there needs to be a hardware limit inside. That's not exposed to the programmer in GPUs, actually. GPU automatically breaks down a block into warps. But assume that a warp, this is what the GPU can execute in parallel. That's the vector length that's not visible to the programmer. Consists of 32 threads. Assume that we have 32,000 iterations over here in this code. And we do one iteration per thread. That means we have 1,000 warps, right? These 1,000 warps each execute 32 threads, and each of them are at the same program counter at a given point. So these warps can be interleaved on the same pipeline. So you can actually do fine-grained multi-threading of warps. I'm going to show you an example. So this is warp 0 at PCX, for example. That's the PC of the load, program counter of the load. This is iteration 0 executed by one unit over here. Iteration 1 executed by another unit. So basically you execute 32 iterations concurrently. 32 of these loads in different iterations. Now, then you may fetch warp 1 at PCX. This actually executes iteration 32, 33, ... up to 63. Fine. I'm going to show you the fine-grained multi-threading of these soon. But if someone tells you, for example, you have warp 20 at PCX plus 2, you can actually calculate which iteration it is executing, right, in the scalar code. Basically, we've divided 32K iterations. We have 1,000 warps. Each warp consists of 32 threads. Warp 20 should be at iteration 20 times 32, right? And then warp 20 should be executing the add, because we said PC at X plus 2, in iterations 20 times 32, 20 times 32 plus 31, right? So all of those 32 iterations will be executed by this warp that's executing this add. And then this warp will move to the next instruction, which is store, because each warp is executing the iteration. Right? Okay, so let's take a look at the fine-grained multi-threading. It's the same example over here. All threads in a warp are independent of each other, so they can be executed seamlessly in a fine-grained multi-threaded pipeline. Let me give you the example. So this is warp 0. So this is a filled pipeline. Initially, you fetch warp 0. Warp 0 executes program counter X, meaning the first 31 iterations and just this load. And then next cycle, no, not next cycle actually, once it's done, it gets refreshed and it executes program counter X plus 1, because it incremented the PC, right, to the next instruction for the next for the same 32 iterations. So warp 0 is always executing iterations 0 through 31, but it gets into the pipeline once in a while so that it can execute different instructions. Does that make sense? So this warp 0 in the steady state, if you will, you can have warp 0 executing these stores at PC X plus 3 across iterations 0 through 31. In the add unit, you may actually have warp 1 at PC X plus 2 executing iterations 32 through 63. In the load unit, because you may have multiple functional units, right? You may have warp 2 executing PC X plus 1, which is load over here, but iterations 64 through 95. And then in the other load unit, which you may have again, or pipeline load unit, you may have warp 3 executing iterations 96 through 127. So you can see that different set of iterations are getting executed on different functional units. I don't even show the decode and fetch stages, but you can have something warp 4 being decoded, for example, and then warp 5 being fetched, right? Because these are doing exactly the same things. They follow through the pipeline nicely, and they're completely independent of each other. So hopefully this makes sense. So this resembles a fine-grained multi-threaded pipeline we had, right? Of course, it was scalar pipeline before, but you just extend it to a vector pipeline in this particular case. Remember, each pipeline stage has an instruction from a different, completely independent thread. We've done that, right? This is the scalar pipeline. Each of them, well, assume that this is kind of pipeline. Multiple functional units are an example of pipeline, clearly. But basically, you essentially have different instructions from different threads. And then you happen to have multiple functional units, many of them, executed concurrently in a SIMD manner. That's the idea. Okay, so hopefully that's clear. We're combining multiple concepts here, and that combination actually makes GPUs even more successful because you can have a very simple scalar pipeline and don't do any dependence checking for branches or any other instruction because you know that the threads are independent of each other. So you take advantage of fine-grained multi-threading and you have lots of threads. Okay, so you remember the lecture on fine-grained multi-thread. So basically, to put things together, again, warp is a set of threads that execute the same instruction on different data elements. This is the SIMT, single instruction multiple thread model. All threads essentially run the same code. Why is it called a warp? Because in English, warp happens to mean this is really actually when you're actually doing manufacturing of a fabric, like weaving this shirt, for example. These are the threads that run lengthwise in a woven fabric. So they basically decided that these are the threads, and each of them execute the same thing. Basically, when you're weaving this, all of the threads are doing the same thing, right? Or you're doing the same thing while you're weaving this. That's the idea, basically. That's the analogy. That's why they call it the warp. So pictorially, this may look like this. You have a thread warp, and you have a common program counter. And a warp consists of a hardware-limited number of threads. That's a function of the hardware that you built. Each of them is scalar. And then you may actually buffer many of them. You may have thousands of them buffered, and then you feed them into a SIMD pipeline internally. In modern GPUs, there are actually tens of thousands of these threads buffered, if you will. So which one do you choose to feed into the pipeline? Well, you need to make sure that the same thread doesn't go into the pipeline until it finishes one instruction in the pipeline. Basically, no two instructions from the same thread should be in the pipeline. That's the basic principle of fine-grained multi-threading, right? That ensures that our pipeline stays simple. We don't do branch prediction, dependence checking. Modern GPUs don't do any of that. No branch prediction, no dependence checking. Assuming that the code is regular and nice. If they want to actually execute more sophisticated code, they may need to do some of that going into the future. Okay, so this is the high-level view of a GPU today. It consists of a bunch of what's called shader cores. I don't know if people really use this terminology anymore, but you may hear this terminology because of the old graphics. Graphics does shading, for example, to actually do manipulation of images that you display on a graphics unit. And then there's a huge, beefy memory subsystem, which we're going to talk about next. Next week, starting tomorrow. But if you look at the shader core, it's a very simple SIMD processor in the sense that you have a bunch of threads that are over here, warps, and then you fetch the warps, and warps are including PC and mask. We're going to talk about the mask soon. You fetch them, you decode them, and then you have a bunch of scalar pipelines that operate in parallel in a SIMD manner. So if you fetched a warp, in this case, let's say you can see 4 pipelines. That means that the warp sizes, hardware warp size is 4. You can actually execute 4 of these same operations in different pipelines, and that warp goes to the pipeline and eventually gets out, goes back to this pool of warps that you can schedule. So what a GPU does today is it schedules these warps into the pipeline, and the pipeline remains very simple. Let me finish this, and then we're going to take a break. So what is the benefit of this warp level fine-grained multi-threading? We've already discussed warps, but basically you have one instruction per thread in the pipeline at a time. So the pipeline is very simple, no interlocking. This gives you a little bit more detail. So you have these warps available for scheduling. You have a SIMD pipeline. And then there could be, we didn't talk about memory hierarchy that much, but in fine-grained multi-threading, memory hierarchy is handled nicely also. If you get a cache miss, you get out of the way. You basically have another buffer over here where you wait, the warp waits, essentially. So here you have warps available for scheduling. Here you have warps that are waiting for data to come back from memory, okay? And the rest is the pipeline that we have seen earlier. So what we do is we interleave warp execution cycle by cycle. Every cycle we fetch from a different warp such that we have only one instance of the warp present in the pipeline at a given point in time. And that hides the latencies. So you may have millions of warps. You may have an, I don't know, 10 cycle pipeline, 10-stage pipeline, and you keep the pipeline busy all the time, let's say. You can actually make the pipeline even deeper, right? As we have seen with vector processing. You can have very deep pipelines. So register values of all threads stay in the register file. We're going to talk about that. It's actually partitioned, like we have seen in vector processing. And fine-grained multi-threading enables two major things. One is simple pipeline, no dependency checking, as we have discussed. But of course, you need to figure out whether you need to wait for memory. And long latency tolerance, meaning you can have many, many warps. While one warp is waiting, another warp is executing. Right? Hopefully, not all warps are waiting. And this is why this is actually a great fit for graphics. You have millions of threads operating on the same large image and video doing the same operations. Okay, recall, basically this is what happens in a GPU. This was a SIMD instruction, right? We had this vector add A, B, C. This is a nice way of looking at a vector processor over here and a combined vector and array processor. We've seen this. What a GPU does is, you have a 32-thread warp executing this code. Add A, TID, B, TID, C, TID. TID is thread ID. So we've converted this SIMD instruction to thread operations. Each element, each thread operates on the elements that are allocated to it, if you will, on a vector. And the execution is essentially the same, if you look at that. You're really multiplexing different threads. That's the idea. That's the beauty of it. There's no difference if you look at the underlying machine. This is SIMD, again, I'm showing you. It's programmed with using this vector add instruction. Here we're programming things with threads, but you can see that the thread ID immediately specifies which elements we're accessing. Okay? Okay, so go back to the vector unit structure that we have seen. This is the vector processor. Recall, we partitioned the vector registers, we created lanes. We said elements 0, 4, 8 are over here. Elements 1, 5, 9 are over here, blah, blah. Okay, sounds good. We have the same structure in a GPU. This is a GPU execution unit structure. Essentially, we have register for each thread. So thread IDs 0, 4, 8, ... have their registers over here. The thread IDs 1, 5, 9 have their registers over here, ... basically. So we partition the register file across threads, essentially. Not that much different. And then recall the vector instruction level parallelism. This picture is going to be very similar. Instead of having these instructions, vector load, vector multiply, vector add, we essentially have warps. Warp 0, warp 1, warp 2, and then warp 3, warp 5, warp 5. And then you eventually get back to warp 0, again, doing some other operation. Right? Hopefully that makes sense. So basically, what I've shown you, hopefully, at this point is that a GPU is a SIMD machine. It's a combination of array and vector processors, except we don't program it that way. Okay, so this is a great place to stop and take a break. Let's take a break until 15:23, and then we'll pick up on GPU programming and a little bit more. Okay, let's get started. Okay. So I think we've got multiple questions. I'm going to tackle one. Are the processing elements pipelined in vector processors? And yes, the answer is yes to that. So if you look at this picture, this is warp execution, and the processing units can be deeply pipelined, just like vector processors are in GPUs as well. Okay, so hopefully everything is clear. Okay, let's talk about memory access very quickly. Even though we kind of talked about it over here, right? This code over here, if you're doing add like this, you need to load the instructions first to registers. So this kind of is an abstract way of looking at the addition, but you first need to do a load. And whenever you do a load, you need to load a particular elements in a vector, or each thread loads particular elements to particular locations in the register file. So if you look at thread 0, it loads elements from iterations 0 over here, right? If you look at thread 1, it loads elements over here. So basically, where you're loading depends on which thread you are, if you will. So let's take a look at this. So same instruction in different threads uses the thread ID to index and access different data elements. That's the key. So if you assume a thread count of, let's say, 16, and you have 4 threads per warp, what you're really operating on is these 16 threads over here, and each of them is essentially operating on 16 data elements. And each warp essentially looks like this. The first 4 threads are loading the data elements at locations 0, 1, 2, 3. The next 4 threads are loading the data elements at locations 4, 5, 6, 7. And then you can keep doing this basically. What we're doing is basically we're partitioning, while we're partitioning the program, iterations across different threads, we're essentially partitioning the array that the iterations are operating on across different threads as well. And each threads are grouped in a warp, so this doesn't change what data each thread is accessing clearly. Hopefully this makes sense. Now this should also, you should also start thinking clearly. We have 4 threads per warp, and each warp is executing the same operations. And if you have a partitioned register file, this thread can execute in a lane that hosts the register file elements 0, 4, 8, 12, etc. Right? So basically, when you want to operate on elements 0, 4, 8, 12, it doesn't nicely fit over here, unfortunately. You basically need to go over here, right? Well, it's nice if it's over here, actually. Sorry, those threads are operating on these elements over here. So when you want to operate on particular data elements, you'd better schedule the threads to those locations. This limits which threads you can combine in a given warp, clearly, as we will see soon also. Okay, but I'm getting ahead of myself. Basically, when you're programming, you need to make sure that you partition the data to different threads. But of course, as we've seen yesterday, I'm not going to talk about this more today, except for some examples later on from real systems. If you want to get the maximum performance, memory should really provide enough bandwidth. So if you, for example, want to execute all of these 4 warps in parallel, you should really be getting 16 different data elements per cycle from your memory. And we're showing only 1 element, for example. If you're adding actually 2 vectors together, then you need 2 data elements for each thread, right? 2 loads, for example. So you really need a significant amount of memory bandwidth to satisfy the computation units, or to supply the computation units with. In other words, the elements per cycle throughput of your memory should match the computation unit throughput. If you have, I don't know, 32,000 add units or 32,000 load units in your GPU, what fraction of them can you actually supply data with? It's good to think about that. This is why with the memory system is a huge bottleneck in these processors, because your computation bandwidth is huge. You can actually do a lot, but can you actually supply the data to those computation units becomes a problem. That's why we're going to dedicate the remaining 6 lectures to the memory system. I should say that in existing GPUs, warps are not exposed to programmers. I mentioned this, but let's clarify this. So you have CPU threads. In GPUs, it's also called kernels, for example. These are sequential or modestly parallel sections on CPU, but you have massively parallel sections on GPU. These are called blocks of threads. So when you program, actually, you have some serial code. So usually it makes sense to execute the serial code on the CPU because the GPU is kind of a waste to execute them. In a later slide, we're going to show you some example where you can calculate SIMD utilization, if you will. We're not going to calculate it, but I'm going to talk about that. So for example, if you have a serial code over here, one thread executing on one data element, if you will, and if you have a warp that's capable of executing 64 threads in hardware, your utilization, if you execute this thread on a GPU, is 1/64, right? 1/64 is a very small number. Your hardware is capable of executing 64 threads concurrently, but now you're executing only one. So it makes sense to actually execute the serial code on the CPU host. And then the serial code may be doing some things. It could be some very dependent computation, or it could be launching of these massively parallel sections. So this simple code may be preparing some massively parallel sections to be launched on a GPU. And this is usually how you launch it in modern GPUs, but there are different GPUs also. So I will not go into a lot of details in programming, but for example, you launch a kernel in GPU. You need to specify the number of blocks you have and number of threads you have in each block. And then you have some arguments. And then these get executed. And then there's some serial code that gets returned to the CPU. And the serial code executes and then launches another kernel. This looks like the GPU execution. This is very similar to the Amdahl's law picture that I showed you earlier, right? So if you're actually doing this sort of computation, hopefully these parallel portions of your program are the dominant part of your execution time. Otherwise, you're going to be limited by how fast you can execute the serial code. And that's Amdahl's law. And don't ever forget that. Right? If the picture looks like this, you're in trouble. If this actually shows a timeline, that serial code is taking too much time, right? As you can see. So it doesn't matter how big of a GPU you have. What you're doing is you're waiting for the GPU to return data. So that's why when you actually offload code to GPU, try to parallelize the serial code as much as possible with the parallel kernel. You try to overlap the serial code with kernel execution on the GPU, overlap computation and communication, for example. You do a lot of parallel programming techniques to minimize the impact of the serial execution, essentially, which I'm not going to go into, but I'll refer you to some lectures if you're interested in learning about GPU programming. It's a good idea, but you can see it. So let's take a look at the sample GPU code and how it looks like in a, let's say, generalized GPU, kind of inspired by NVIDIA, if you will. It's very similar to CPU code, and that's what has made it very successful. So this is CPU code, similarly to what I showed you over here, right? This is, you're adding two different vectors and putting the results in another vector. Basically, you have 100,000 threads over here, and you just need to specify a thread ID that's computed using blocks and some thread ID X, which I'm not going to go into. But basically, you specify a thread ID, and that thread ID gets communicated to the GPU. But if you look at this code and this code, there isn't much difference over here. You just add a thread ID over here as opposed to an induction variable II. The reason is this is programmed using threads. Each thread executes an iteration. There's no scalar code that has multiple iterations, if you will. Okay, so this is a little bit more sophisticated. But again, the whole point I'm showing you this is not because you should understand what's going on exactly over here, but to show you how similar these two programs are to each other. Right? This is a CPU program. You're doing matrix addition. You're adding two matrices. Essentially, this is the scalar program, two loops. You can see that. And this is the GPU program. In GPUs, you basically care about the thread ID over here. So these are the indices over here. And then you call this from this main code, add matrix. You basically need to specify the block, the number of blocks you have, and the number of threads you have. Okay, again, I don't expect you to learn about GPU programming. The whole purpose over here is really to show that these codes are very similar. Whereas if you look at CPU and SIMD, they're very different from each other. You don't program it this way. Okay, So if you're interested in GPU programming, you can watch a lot of lectures. In fact, we have a heterogeneous systems course that we hold every semester that goes into a whole lot of detail about how do you program a GPU, how do you make it work for different algorithms, how do you get high performance, very, very interesting stuff, not the subject of this course. Okay, so let's talk about, I said these blocks. So how do you get from blocks to warps? So if you look at a GPU core, it's a SIMD pipeline essentially. In a modern GPU, it's called a streaming processor. Again, you may hear these terms. They're fancy terms, but essentially a streaming processor is a SIMD pipeline. And a modern GPU has many such processors. It's called a streaming multiprocessor. I'm going to show you a breakdown of later old and new GPUs soon. But it looks like this. So this is one of NVIDIA's architectures, if you will. You can see that they call it a streaming multiprocessor. There's an instruction cache. There's a warp scheduler. There are multiple warp schedulers. There's a huge register file. And these are the streaming processors. When you see these are SIMD units, essentially, SIMD pipelines. SIMD pipeline means you actually have a bunch of scalar pipelines operate in a SIMD manner, like we have shown earlier. And then you can see that there are lots of load store units and some special function units. And then there's a cache hierarchy. So you can see the parallelism over here. I'm going to show you more numbers later on. But basically, when the programmer specifies the blocks, these blocks are divided into warps and sent to SIMD unit. So each SIMD unit, the width of this specifies the warps. So you may actually have 32 threads in a warp, for example. And then you may actually have different blocks specified by the programmer. So blocks are specified by the programmer. These are blocks of code that do essentially the same thing using different threads. And these blocks are divided into a bunch of warps. Block 0 has some warps, block 1 has some warps, block 2 has some warps, etc. And they get basically scheduled onto streaming multiprocessors, if you will. Again, I don't expect you to know what exactly blocks are, but you should really know how warps are executed. There's also block scheduling that we're not going to cover over here. Okay, so without going into further detail and complicated things, let's talk about the advanced and disadvantages of warp-based SIMD versus traditional SIMD again. And then I'm going to show you a particular advantage that we cannot get with traditional SIMD, another particular advantage. So traditional SIMD really contains a single thread, right? This is really sequential instruction execution in the end. You have lockstep operations and SIMD instruction. We've discussed this. Programming model is SIMD. There are no, so what does this mean? We've discussed, as I said, basically, you have a SIMD operation, you have a vector load, for example. When you do the vector load, you need to finish that vector load. You need to finish every single element of that vector load before you can move to the next instruction. Yes, you can pipeline instruction. Yes, you can do data forwarding. In fact, you can actually out of order execute these instructions. You can combine the concept of SIMD with out of order execution. It's going to be a quite heavy, extensive hardware costly processor, but you could do that, okay? But traditional SIMD doesn't do that, let's say. Programming model is SIMD. There are no extra threads. Software needs to know the vector length. That's what we've discussed earlier. Instruction set architecture needs to change significantly. You need to have vector and SIMD instructions. On the other hand, warp-based SIMD alleviates a lot of these issues. Instead of having a single thread, you have multiple scalar threads executing in a SIMD manner. Same instructions executed by all threads. It doesn't have to be lockstep. Each thread can be treated individually. In fact, you can take one thread and place in a different warp. This is not visible to the programmer. Programming model is not SIMD, basically. SIMD is very strict. I'm doing a vector load on these 64 elements. Done. You cannot move. You cannot operate individually on each element unless you do masking, right? Here, you can actually move the threads, as we will see soon. So software doesn't need to know the vector length. And this enables multi-threading and flexible dynamic grouping of threads. And also, ISA is scalar. SIMD operations can be formed dynamically. You don't need to have special instructions for vectors, essentially. Essentially, as we've discussed earlier, this is SPMD programming model implemented on SIMD hardware. So let's go back to SPMD again. This is single procedure or single program multiple data. This is really a programming model rather than computer organization, as we've discussed. Each processing element executes the same procedure except on different data elements. And procedures can synchronize at certain points in the program, in barriers, for example, which we're not going to go into also, but you've seen it when we talked about data flow. Essentially, multiple instruction streams execute the same program. So what's the difference between these instruction streams? Each program or procedure works on different data and can execute a different control flow path at runtime. So this is interesting now. I've given you very simple examples, but if you actually have a thread branching but on a condition. It tests the data element, and based on the data element, takes one path. Another thread in the same warp may take another path, right? Because you're testing different data elements. You're testing, for example, if the data element is greater than 0. One thread may test that to be true. Another thread may test that to be false. Now these diverge, meaning they're no longer at the same PC. Now you have a problem, right? You've grouped these things together, they're operating on the same PC, but when they execute a branch instruction, they diverge. So what do you need to do? You need to mask some of them out. Meaning you may treat them actually as still executing the same PC, but some instructions, some threads should not be executing that operation based on something very similar to a vector mask, like we've seen, right? That's the idea, basically. But you can also do something even more sophisticated, as we will see. So clearly, when you mask something out, you have some warp, let's say 64 threads that can be operated, that can be executed concurrently. If one of them is supposed to execute the instruction and the remaining 63 is not supposed to execute the instruction, because that's how the data values are, you say if array A thread ID is greater than 0, and only one of them evaluates to true, you're basically wasting those huge execution units, right? Only one of the threads will do something useful, all of the 63 will do something useless, meaning your SIMD utilization is 1/63, okay? We're going to calculate that again. So, okay, I kind of got ahead of myself, but this is really important about control flow. We're going to see this pictorially soon. So, but to pull back, many scientific applications are actually programmed this way, and they run on MIMD hardware. This programming model, actually SPMD, is quite popular even before graphics. People programmed large-scale vector instructions this way, and if they don't have a vector, large-scale, let's say vector operations this way, and if they don't have a vector processor, they cannot afford it, they run on multiprocessors using MIMD hardware. So modern GPUs enabled these programs to actually run on SIMD hardware to be more efficient. And what's the difference? If you execute the same thread across many, many different processors, you have overhead. What is the overhead? You fetch the same instruction, decode it, execute it, fetch and decode. You basically do the same fetch and decode operation across many processors. In a SIMD processor, you don't do that. You fetch and decode only one instruction and enable many operations. That's the difference between MIMD and SIMD hardware. If you execute this programming model on MIMD, multiprocessors, it's much more expensive in terms of energy, for example, and also potentially performance. Whereas in SIMD hardware, it's cheaper because you've saved the area as well as energy. Okay, I've shown you this example before, right? So I will not go into this again, but let's talk about this second part. You can group threads into warps flexibly in a GPU. In other words, you can group threads that are supposed to truly execute the same instruction. This way, you can dynamically obtain and maximize the benefits of SIMD processing. So let's take a look at this. Now, more complicated example. Each thread can have conditional control flow instructions, as I foreshadowed. Threads can execute different control flow paths. So this is our complicated code. Each thread has this code. So it's the programming model is still SPMD. Each thread is doing the same thing, except on different data elements. So thread 1 may happen to take this path, right, in this code. Thread 2 may happen to take this path. Thread 3 may happen to take some other path. And thread 4 may happen to take a completely different path. You group them together. Initially, they're all executing A. Initially, they have a common PC. So how do they execute over here? Let's take a look. So essentially, there's a problem because threads execute different control flow paths, but some of them are not supposed to execute those instructions that they're at, right? So in a SIMD processor, we handle it through masking, if you remember the masking. We're going to handle it in a similar way over here, except it's going to be purely hardware-based. So we've already discussed this, right? A GPU uses the SIMD pipeline to save area on control logic. You group scalar threads into warps. This is a more simplified code, if you will. So this problem is called the branch divergence problem. When threads inside warps branch to different execution paths, you have divergence inside the same warp across different threads. So let's take a look at this. Let's assume that we have 8 threads in a warp. I hope this is 8. Initially, they're at the same program counter. That's good. They all are supposed to execute this, right? And then they all are supposed to execute the branch instruction. That's good. Once you go to the branch, some of them execute this path. Now, what happens to threads over here? They're masked out. So when you execute this branch instruction, you also create a mask saying that, oh, the threads that are going to this PC, the ones that are actually executing, the ones that are supposed to execute this program counter have a mask bit of 1, essentially. And this is created by the hardware, stored together with the warp. Essentially, this is a different warp right now. You actually have the same PC, but also a mask. What identifies a warp is not just the program counter anymore, it's also a mask associated with it. Okay, so that's one. And then the path B has another program counter, another mask over here, right? And then eventually there's some logic in GPU that figures out that these merge. And then they actually form a single warp at that point. And then the PC is the same, and then the mask is all ones clearly, right? Okay, so I'm not going to go into the details of how they merge, but there's some hardware that does this nice. And more, actually, there's some hardware that does more. So this is basically the what we've seen earlier, right? This is actually conditional execution or predicated execution or masked execution. We've done something very, very similar in vector process, except it was not flexible. The programmer needed to handle this using vector masks. Here, the programmer doesn't need to handle it. Hardware is handling it. Yeah, vector mask and masked vector operations. Okay, let's talk about what else can we do over here. Now, take a look at this picture. This picture is showing a small number of threads, 8 threads. Now imagine that you actually have millions of threads. Yeah, millions of warps over here. What a GPU can do is, a GPU can examine which ones are at which program counter and merge the different threads to populate the warps as much as possible where the masks are all 1, right? That's the idea. And existing GPUs do that. So if you have many threads, you can find individual threads that are at the same PC. You need some hardware support to do that. And group them together into a single warp dynamically. This reduces divergence. In other words, it improves SIMD utilization. So let's go back to the SIMD utilization. So if you look over here, in this cycle, the SIMD utilization is 100%. All threads are executing this operation. Here it's 100%. Here it's 50% immediately. Here it's 50% also. Here it's 100%. So we want to actually have 100% all the time, right? Ideally. If you have many threads, you can get closer to 100% by grouping threads together. Okay, SIMD utilization is essentially the fraction of SIMD lanes executing a useful operation, executing an active thread. An active thread is a thread whose mask bit is 1, okay? Who's really supposed to execute that program counter. So this is the idea of dynamic warp formation or merging. The idea is to dynamically merge threads executing the same instruction, in other words, at the same PC. For example, after branch divergence, but there could be other applications. Essentially, you form new warps from warps that are waiting. This is why you have a lot of warps that are waiting, and you can examine them. And enough threads branching to each path enables the creation of full new warps. Full new warps meaning a full warp is essentially a warp with 100% SIMD utilization. All of them are active. So let's take a look. So these warp X and warp Y are waiting. They're not in the pipeline. And you have these masks. These are the masks, basically. These threads are supposed to execute in warp Y. These threads are supposed to execute this instruction in warp X. And the GPU figures out that, oh, these can be combined like this. And if I can combine into one warp, so I execute only this warp. And it's nice because the SIMD utilization of this is quite high, higher than both of them. Okay, that's the idea. So similarly, you can combine these two. Unfortunately, here you cannot eliminate a warp. Why? Because you can see that these two threads in these two different warps have to be in the same lane. Remember, you partition the register file. You cannot move. You cannot move this over here. You cannot move this over here also because these are the lanes. So the location of a thread in the warp determines where you go in the vector lanes, in the SIMD lanes. As a result, if you move this over here, you're not going to access the correct register. Hopefully that makes sense, right? I'm going to ask you a question later on that basically I have answered right now. Okay, so but if you have more warps, you can do that. So now you can actually combine 3 warps into 2. So if you have a million warps, you actually can be in luck. You can combine many of them together. That's the beauty of this sort of execution model. So this is the idea of dynamic warp formation. Let's take a look at this example. You get to this branch that we saw earlier. You get to this path. But then if you have another warp, that warp is supposed to execute this path. So these two warps are executing the same path. And you can combine them, right? Like this. In this case, you didn't say much. But let's take a look at a more complicated example relatively quickly, since we don't have a lot of time. But basically, this is an example that I will actually let you study on your own. We have two warps, warp X, warp Y. Each of them has 4 threads. And these are the masks you can see. And in the baseline, they execute like this. So we're interleaving the two warps together, as you can see. And you can see that the SIMD utilization drops down where the masks are 0001, for example, right? So you can do this on your own. It's beautiful. And then eventually SIMD utilization goes back up because masks become 1, 1, 1, 1. So basically you have divergence and then you converge at the end. Now, this is the baseline. If you don't actually try to actively combine the warps together, this is the amount of time you will take to execute this. But now you can create a new warp from scalar threads of both warp X and warp Y executing at some basic block. So in this basic block D, for example, it will look like this, assuming you can combine them in time. So in dynamic warp formation, what you can do is you combine the ones that are at B. You need to do it before feeding them into the pipeline, of course, right? Because once you execute, you figure out the warps, you figure out what the next instruction will come and what is your mask. And then you can actually do this before you feed the warp into the pipeline again. You can see that B is combined nicely, but unfortunately, one of them cannot be combined because they conflict. As a result, this is a poor warp that's with low utilization. But these two C's can be combined. You can see that instead of having two warps with 25% utilization, you have one warp with 50% utilization. These two D's can be combined, as you can see. And then E's can be combined, but you don't save one warp. F's can be combined, you save one warp. And then the rest is 100% anyway. So basically, you can see that you save cycles. First of all, you save time to execute the same operations on this number of threads, but you also save efficiency. You're not wasting some functional units. Okay, so as I said, you cannot group this thing arbitrarily. If two threads are accessing the same register file, you cannot put them together in the same warp. So flexibility is limited, basically. Can you move any thread flexibility to any lane? The answer is no. You can move threads to a lane only if there's no other thread in that particular lane in a given warp. Right? That's the idea. So there are hardware constraints. Okay, analyzing GPUs is fun. It's so much fun that you can do it in your exam, and probably you're going to do it in your exam in August sometime. I will not go through this because I'll let you have the fun. Basically, we almost always have this sort of question. Once you understand how this idea of divergence is working, which instructions are being executed, which instructions are not being executed in a thread, this is relatively easy to solve. Okay, this is just foreshadowing. Let me see how much time we have. Okay, we don't have a lot of time. So I'll go through this relatively quickly. You're not responsible for this, but we've actually been working on GPUs a long time ago when GPU microarchitecture was really, really important to look at. So branch divergence is very interesting, but there are other issues. Long latency operations are actually a problem in GPUs also. So even though you may have so many threads, you need to schedule them appropriately. That's why that scheduler, warp scheduler, is really, really important in a GPU. So this is a work that we did with NVIDIA, and the idea is used in a lot of NVIDIA GPUs today. I believe all of them. But the issue is you may have all warps. Once you get the long latency instruction, this actually foreshadows the next lectures also. Once you get the long latency instruction, these all need to wait. And if all warps arrive at the same long latency instruction at the same time, your whole machine waits. And this is a problem. And the model that we've discussed, the single program multiple data model, is actually very amenable to this problem. Because everybody executes and eventually everybody gets to the same load and they all wait. So if you do the scheduling this way, such that all warps come to the same instruction at the same time, this is not good. You need to wait a long time. So one of the ideas in this work is to do the scheduling at a smaller granularity. Essentially schedule some warps and then schedule the other warps such that they reach the long latency instruction in a distributed way as opposed to at the same time. That's the idea. Again, I don't want to go into the details of this. There are many, many interesting ideas here, but this saves a lot of cycles. So internally, the GPU does a lot of interesting things, basically. That's my whole point. Internally, GPU does scheduling of warps at a smaller granularity. So this is, I'm going to skip over here. If you're interested, you can look at it. But this shows that by having a large warp and breaking to subwarps, you can actually find a lot more parallelism internally, such that you can keep these subwarps filled, such that you increase the SIMD utilization. Again, I don't have time to talk about it because I want to talk about some real GPUs relatively quickly. So this is just to foreshadow that there's a lot of interesting things going on in GPU systems. Now, let me give you an example GPU at a high level very quickly. Since you have a version of something like this in your cell phones, well, this is an old one. So you actually have something much more powerful over here. So this is an example GPU. Over time, they become beefier and beefier. So this GeForce GTX 285 had 240 stream processors. I've already defined stream processors. Essentially 30 streaming multiprocessors and 8 SIMD functional units per core. That's what they had essentially. So this is small by today's standards. Even small, it looks big. So you can take a look at this core, which has 8 SIMD functional units. You can see that requires a lot of registers, actually, 64 kilobytes of registers. And then there's the memory hierarchy, as we will discuss starting tomorrow. But you can see the SIMD functional unit. It can do multiply and add and multiply, etc. Okay. So essentially, their warp size was 32 threads. They were able to group 32 threads to share an instruction stream. Each group is a warp, essentially, as we've discussed. And they were able to interleave up to 32 warps in a fine-grained multi-threaded manner. Essentially, you have 32 threads in a warp, and then you have 32 warps. Your pipeline is much smaller. It could be 5, they don't disclose it, but it could be 5 or 6 stages, for example. So you actually have a lot more warps than you can feed into the pipelines. So you can feed into the pipeline stages. So up to 1024 thread context can be stored. That's why you have a huge storage in the register file. And it employs everything that we've discussed, partitioned register file, different lanes, etc. And this is what happens if you scale up to 30 cores. So 30 times that is 30,720 threads. That's a lot, as you can see, right? But this is nothing compared to what I'll show you soon. So evolution has actually, this is what we've seen in 2009, GTX 285. And this is the number of functional units. And this is the gigaflops. I'm going to change the slide later on. Essentially, it's been increasing. You can see that people have been adding beefier and beefier GPUs. So this is V100, which is essentially here. They increase the stream processors to 5,120. Essentially 80 cores and 64 SIMD functional units per core. Each core is more powerful in terms of SIMD, and you have more cores. And they also added these tensor cores for machine learning, which I will briefly talk about. This is essentially very similar to advanced matrix extensions, for example. It's a specialized unit for matrix multiplication. So the block diagram looks bigger, as you can see. Later, we're going to see the memory system, and the memory system is getting bigger and bigger also. And you can see actually the teraflops, tera floating point operations per cycle is increasing significantly. And you can see that the tensor cores, the reason they added these specialized tensor cores for matrix vector multiplication is because they cannot get enough bandwidth, computation bandwidth using the more general purpose cores, right? This is again, specialization versus general purpose. So if you look at these tensor cores, they look like this. In this case, this is a little bit old, but basically there you can do matrix multiplication using floating point values, etc. Nothing that you haven't seen. This is the tensor core microarchitecture. Again, I don't expect you to know all of these, but you can see that even a GPU is not enough to do specialized computation because it's general purpose. If you want to do specialized computation, you add the specialized functional unit. It's called a tensor core over here. So in each tensor core, interestingly, they have other SIMD units, 16 SIMD units per tensor core. And essentially, in each cycle, they can do 4x4 matrix multiply and accumulate. You can read more about it. Now, there's some differences from conventional SIMD. They can share registers inside the warp, inside this tensor core. That helps the programming easier. And so that helps efficiency also, which I'm not going to talk about here also. So there are other TPUs also. Basically, the reason is they're building these specialized accelerators for machine learning, and the reasons you know. I'm not going to talk about this, but you can learn more about this on research lectures. Some of those are, so the Google's TPU was systolic array-based, right? So this is a different approach. If you look at this tensor core, this is a very different approach than the TPU. Okay, let me give you where we're getting towards. This is A100. This is still not the state of the art, and it's increased even more. You can see that there are new data types being added, tensor data types, floating point data types, and then support for sparsity because you operate on actually many matrices that have 0 values in machine learning. So they actually have mechanisms to not operate on 0 values. That's the one way of actually accelerating machine learning. Ignore zeros as much as possible because you have a lot of zeros in some of these computations. So this looks much bigger, as you can see, and the numbers have all increased. So it was 125 teraflops. Now it's 312, for example, for deep learning. And the tensor core is beefier, and also the GPU is beefier. And this is, I believe this is the state of the art right now, H100. I can stand to be corrected, of course. You can see that the teraflops is actually much higher over here. This is general purpose teraflops, not the machine learning teraflops. And the functional units are much higher. So you can see that they've been increasing. So machine learning teraflops are actually getting to the next place, which is exaflops, right? Is that correct? Peta, tera, no, peta? I don't know, you figure it out. Okay, so you can see that people are adding more data types. Why? They figured out that operating on 16-bit data, 32-bit data, floating point is expensive. We can actually do machine learning inference and sometimes training on smaller data types because we don't waste a lot of computation. So they've added these floating point 8 units, for example. So they actually play a lot of tricks. You can see that people are trying to make this accelerator much more efficient. Now, this is an interesting combination. Even if you look at a GPU, it's not a SIMD machine anymore. It's a heterogeneous architecture, right? It has SIMD, and it has this tensor core accelerators, if you will. I'm going to end this with this food for thought. So GPUs and systolic arrays, these are actually things that are both used for machine learning acceleration right now, but even GPUs employ SIMD for tensor cores. There are many questions over here that are not answered yet. So it's good to think about the trade-offs. And again, I will mention that if you're interested in these things, you may be actually interested in taking future courses because these things are things that we cannot cover in one course. Okay, we've already, but also if you're really interested, I would recommend looking at other courses as well. Let me conclude over here. Tomorrow, we're going to switch gears and talk about the memory system, which is really what makes all of these things work. If you don't have a memory system, a GPU would be useless to you. I think people are still wanting to continue, but I don't have anything else to talk about. Any questions? I should remind you maybe to fill the evaluations. I read all of these evaluations, and we actually improve the course with feedback over time. So take time to fill the evaluations. I'll remind you again, but since everybody's waiting over here, I'll remind you right now. Okay, have a good afternoon. I'll see you tomorrow. Take care.